Hello everyone again. This is lecture 5 part 2 of current electricity. In this lecture we will move on with our further discussions on cells, EMF and internal resistance only. In the previous lecture we understood the concept of how the EMF has been produced or what is actually the definition of EMF. Similarly, we also understood the concept of internal resistance, in which internal resistance is nothing but denoted by small r, which is a type of resistor only which has been implemented so that we can understand the actual nature. In ideal terms we generally take the value of small r as to be 0, but in real life terms there will be always a resistance due to devices also. There has not be a particular ideal case in which only a capital external resistance R will be used for the energy dissipation. The energy can be dissipated by the device also. So, even let us suppose there is a complete small circuit with a bulb and a capital resistance R and a battery cell. Let us say I denote the battery cell by B. So, here the resistance will be due to the bulb also denoted by internal resistance small r and the resistor capital R also. Therefore, we just need to understand this concept that there will be an internal resistance happening and it is denoted by small r here. Okay. So, I am Sameer Lavankar. Let us begin our discussion on this concept further. So, right now we are on the 11th concept here, that is cells, EMF and internal resistance. So, let us start our discussion on that portion only. So, these all things are being understood in the previous lecture only. Let us move on with today's discussion now. Thus, EMF epsilon is the potential difference between the positive and the negative electrodes in an open circuit, that is when no current is flowing through the cell. So, this is just the theory part, that what is epsilon being defined as? It is nothing but the potential difference between the positive and the negative electrode, that is when no current is flowing through the cell. Okay. If however capital R is finite, so now the previous complete data case till here was about where if we assumed that the value of capital R was infinite. Now we are understanding the concept that if capital R is finite, so what happens now? So if however capital R is finite, I is not 0, quite evident I cannot be 0 now, because we can understand this concept as I is equal to V by R, and because the value of capital R is not very high or not tending to infinity, therefore I cannot be 0. Therefore, if I cannot be 0, then that means that there will be a finite value of current also. Okay. So, I is not 0, in that case the potential difference between P and N is, so it is nothing but V plus V minus IR. Why there is a minus IR? Because there is a decrease in the potential difference. Why there is a decrease? Due to the current passing through. So, we can just write this as V plus V minus IR, which is equal to epsilon minus IR here. Okay. So, note the negative sign in the expression IR for the potential difference between A and B. This is because the current flows from B to A in the electrolyte. So, previously also we understand that the current which is flowing from resistor is P to N, but the current which is flowing from electrolyte is N to P. So, because there is a decrease, there is a change there, therefore, we try to apply that change concept or reverse in direction by using a negative sign here. So, therefore, we will find that the value of potential difference is nothing but epsilon minus IR. Okay. In practical calculations, the internal resistance of cells in the circuit may be neglected when the current I is such that epsilon is very greater than IR. Please make sure here R is nothing but internal resistance, not the value of capital R due to this, because there is an internal resistance which we are assuming for the electrolytic cell, that is why we are assuming a value of I into small r, not I into capital R. There is no dissipation of energy being assumed due to the potential difference, due to the resistor capital R, it is only assumed due to the resistor small r here. Okay. So, this thing has been explained. Now, in practical calculations, internal resistance of a cell in a circuit may be neglected when the current I is such that epsilon is very greater than IR. The actual values of the internal resistances of cells vary from cell to cell. The internal resistance of dry cells, however, is much higher than the common electrolytic cells. So, this is just for your theory portion here, you just need to remember this, and the internal resistance of dry cells is much higher than the common electrolytic cells. I will not go into much detail of why they are higher, why they are lower. For now, for a 12th class, you just need to remember this, that the internal resistance of dry cells is much higher than the common electrolytic cells. And similarly, we can just for practical calculations we can assume that internal resistance can be neglected such that only and only when the epsilon value is very greater than IR. It is quite evident only because if it is very high, then we can assume this is approximately equal to epsilon. So this thing only. So hence if we are assuming this epsilon, we are assuming that epsilon IR is approximately equal to 0, and hence it can be neglected. Okay, so this thing is the end of this concept also. Now we also observe that since capital V is the potential difference across capital R, we have from Ohm's law V is equal to IR. So as we know that the potential difference across this portion is also equal to V, and potential difference across this portion is also equal to V. But here the potential difference V is nothing but I into capital R. And the previous portion, in this we understood that potential difference is nothing but what we can say epsilon, that is V plus V minus IR. So just now equating these two equations, let us try to see what comes into picture. So it is nothing but capital IR is equal to epsilon minus capital I into small r. So it is nothing but epsilon is equal to capital IR plus capital I small r, that is equal to capital I into R plus R. Hence we got that the current is nothing but equal to epsilon upon R plus R. So this is the final conclusion what we understood from this complete electrolytic solution experiment or it is a model. So this thing also can be explained in this way. Let us suppose the EMF produced or the voltage produced by the cell be let us say epsilon, and the resistors are in series here. So if the resistors are in series and let us suppose this is R, we can find the equivalent resistance to be nothing but equal to capital R plus small r. So this thing can be just kept analogous to this portion which has been calculated here. Okay, so this thing I will explain. So finally what we got is nothing but capital I is equal to epsilon upon capital R plus small r. Okay. So we also observe that since capital V is the potential difference across capital R, we have from Ohm's law V is equal to IR. So this thing has been explained. Now combining above two equations, we get capital IR is equal to epsilon minus IR, same as this form here, or finally capital I is equal to epsilon upon capital R plus small r. So this is the final conclusion end of this complete concept here. So you just need to remember what? You just need to remember that capital I is equal to epsilon, that is the potential difference or electromotive force upon capital R plus small r. Okay. So this thing is also been explained now. Next, the maximum current can be drawn from a cell is for capital R equal to 0. So let us suppose, so because we cannot change the internal resistance value because that is inherited in the device. So finally what we can change here is nothing but capital R value. So if we need to find out the maximum current for the initial what we can say for the instant at which we are finding out for a constant battery that having a potential difference of epsilon, then that maximum current is nothing but epsilon by small r. So this thing has been explained, and it is I max is equal to epsilon by r, the same thing which I just uttered. However, in most cells the maximum allowed current is much lower than this to prevent permanent damage to the cell. However, because we just need, there has to be some limitations on the amount of current also passing from point A to point B. So therefore we always try to import or impart some resistance capital R by externally also. We do not want that maximum current to take into picture. So however, in most cells the maximum allowed current is much lower than this to prevent the permanent damage to the cell. So that is the end of your cell's EMF and resistance. Let us move on to one of the examples in this portion here only. Okay. So first of all, please look over the diagram here. So as you can see a diagram, let me try to first explain you the diagram here. So there is a 16 volt battery. So there is a 16 volt battery, as you can see this is a plus positive sign here, negative sign here, that means the direction of current will be nothing but in this sense. It will go in this sense like this and it will end it like this. Okay. So this thing has been explained. Then similarly as you can see that there is a 1 ohm resistor here. I guess this 1 ohm resistor tells you about the internal resistance. We will see in the question. For now we are just, I am just assuming it. And similarly there is a complete series of resistors in kept here. So it is nothing but, so as you can see this 4 and 4 ohms are in parallel, this 1 ohm is here and 12 ohm and 6 ohms are in parallel. So if I need to calculate, I think the first question is about equivalent resistance only. So if I just need to calculate this, so first of all I will try to calculate the equivalent resistance from this 4 ohms and 4 ohms. So that will be nothing but 1 by 4 plus 1 by 4 is equal to 1 by R. Hence I will get R equivalent is nothing but 2 ohms. So I can just write it here directly. So it is nothing but 2 ohms here. Similarly this is 1 ohms here, and similarly for this we can just find out by 1 by 6 plus 1 by 12. So finally I guess we will get the value equal to 4 ohms. So this is 4 ohms here. So if you need to find out the equivalent resistance, it will be nothing but a simple addition of these all, and that will be find out as 7 ohms, and hence this is the equivalent resistance. Okay. So now let us move on with the discussion now. What is the question being asked here? So a network of resistors is connected to a 16 volt battery with a internal resistance of 1 ohms. Internal resistance, yes, so I was correct. So this is nothing but the internal resistance, small r, as shown in the figure. Compute the equivalent resistance of the network. So the first question is nothing but this only. So let us look at the solution now. So network is a simple series and parallel combination of resistors. The first two 4 ohms resistors are in parallel and are equivalent to a resistor which is equal to 2 ohms. Similarly, in the second same way, the 12 ohms and 6 ohm resistors are in parallel and equivalent to a resistor which is 4 ohms. So this thing also been explained. And finally, the equivalent resistance capital R of the network is obtained by combining these two resistors and with 1 ohm. So it is 2 plus 1 plus 3, sorry, plus 4, which gives you equal to 2 plus 4 plus 1, which is equal to 7 ohms. So finally the answer for the first question is being obtained, that is the equivalent resistance of the network is nothing but 7 ohms. Okay. So this thing has been done. Let us move on to the next question now. Next is obtain the current in each resistor. So what is the current in each resistor? So as you can see, quite evident, please look over the question here carefully. So as you can see, if the current is I passing through it, then there will be some current I1 passing through this 4 ohms and current I2 passing through this 4 ohms here. But this I is equal to I1 plus I2. Also from the symmetry of the diagram, this can be obtained that the amount of current passing through the 4 ohms will be nothing but equal to the current passing through the another 4 ohms resistor. Therefore, we can assume that I1 is equal to I2, and therefore I1 is equal to I2 is equal to I by 2 using these two equations. Hence, we can get the value of I1 and I2 if we know the value of capital I. Similarly, for the 1 ohms here, as the current is passing capital I only, therefore we can directly find out the value of capital I for this. So if I just keep on writing here, so the resistors having the current, here it will be I by 2, here also it will be I by 2, here it will be I, and now we need to calculate for this portion here. So now as we know that the potential difference across both the resistors will be same, so we can just write that the current passing through 12 ohm be I1, we know the value of resistor, that is 12, is equal to I2, you know the value of resistor, which is 6, as the potential difference is same, as the both are having the same potential difference. Therefore, using this we can find out that the value of I2 is nothing but 2 I1. Also using this as equation number 3 and equation number I1 plus I2 is equal to I, we can obtain that value of I1 is I1 plus 3 I1 is equal to I, or I1 is equal to I by 4. Similarly, I2 is equal to nothing but 2 I1, that will be equal to I by 2. Sorry for the mistake. So finally we will got the two currents equal to I by 3 and 2 I by 3. So finally what can we obtain? So it is nothing but these are the currents which are passing through these all resistors. So let us now look over the solution of this problem here. So finally the total current I in the circuit is epsilon upon capital R plus small r. So this has been obtained in the previous concept discussion of this cells EMF and internal resistance only. So finally I is nothing but epsilon is given to you as 16, the complete resistor capital R is nothing but 7 and 1 ohm is given, therefore it will be 7 plus 1 which is equal to 8, 16 by 8 is nothing but 2 amperes. Hence we found out the value of total current equal to 2 amperes. Now consider the resistors between A and B. If I1 is the current in one of the 4 ohms resistor and I2 is the current in the other, then I1 into 4 is equal to I2 into 4. Why? Because the potential difference across both are same. Therefore, I1 is equal to I2, which is otherwise obvious from the symmetry of the two arms. Now I1 plus I2 is equal to I is equal to 2 amperes. Therefore, the current through this 4 ohms will be 1 and through this will also be equal to 1. Thus, I1 equal to I2 equal to 1 ampere, that is the current in both 4 ohm resistor will be 1 ampere. So this thing has been explained. Now the current in the 1 ohm resistor between B and C will be 2 amperes, so this thing also been explained. Similarly, now consider the resistance between C and D. If I3 is the current in the 12 ohm resistor, if let us suppose the current here is I3 and I4 is the 6 ohm resistor, and let us suppose the current in this is I4 here, then I3 into 12, it is again thus the potential difference constants, that the potential difference across these two lines, these two portions will be same. Therefore, I3 into 12 is equal to I4 into 6, and therefore we will get I3 plus I4 equal to 2 amperes. Therefore, I3 is 2 by 3 amperes and I4 is 4 by 3 amperes. So, that is the final assumption, or that is the final conclusion which we got from this complete concept here for the B part. Thus, the current in the 12 ohm resistor is 2 by 3 amperes and the current in the 6 ohm resistor is 4 by 3 amperes. So, that thing also has been explained here. So, A part is also done, B part is also done. Let us move on to the C part, that is obtain the voltage drops VAB, VBC and VCD. So, first of all we should know that the complete the complete voltage due to all will be nothing but the complete 16 volt supplied here. The 16 volt will be divided into these three portions. How they will be divided is nothing but the use again of Ohm's law only. There is no different or complicated concept here. So, just look over here carefully and just simple mathematical formulation will give you the result. So, the voltage drop across AB will be nothing but the I into capital R can be taken as the equivalent resistance here. So, I1 into 4. So, either we can take I1 into 4, that is I1 is nothing but the resistance into capital R here will be 4 here. So, that will be equal to I1 we calculated in the previous section to be equal to 1 and the resistor was equal to 4, hence we will get the value as 4 volts. Similarly, we can do for the complete check box also. So, complete current which is passing into the resistor capital R equivalent here. So, we knew that the capital current which is passing is 2 amperes and the resistor which is 4 and 4 in parallel, which gives you 2 value here, hence it is again calculated as 4. So, as you can see both the calculations are same. Okay. So, VAB is nothing but I1 into 4 which is equal to 4 volts here. This can also be obtained by multiplying the total current between A and B by equivalent resistance between A and B, that is V equal to 2 into 2. So, this is the same thing which I obtained here. Okay. Next, the voltage across B and C BC will be nothing but 2 into A again. So, as 2 amperes are passing through this and multiplied by resistor which is 1, which gives you again 2 volts. Finally, the voltage across CD will be nothing but 12 into I3. I3 is obtained in the previous discussion here to be equal to 2 by 3 amperes, hence just multiplication gives you 8 volts. Next, we can find out this can alternately be obtained by multiplying total current between C and D by equivalent resistance between C and D, that is VCD is equal to 2 amperes multiplied by 4. So, the equivalent resistance for this was nothing but 4 ohms. So, we can multiply this 4 into 2 which gives you 8 volts again. Note the total voltage drop across AD is 4 plus 2 plus 8 which is equal to 14. Please look over this concept very carefully because it is a new concept now. As you can see that the passage of battery, the complete voltage difference of battery is 16 volts, but you can see clearly that let us suppose we do not know the concept of internal resistance. We supply a 16 volt battery and suppose that there will be a passage or there will be a distribution of 16 volts in all these three series of resistors, but when we try to find out the value of resistors here, we found that the complete value of potential difference is not being distributed to these three resistors. So, when the concept was being found, it was found that there is another resistor smaller also being kept which takes that 2 volt into picture into itself. Therefore, there was not the distribution and hence the origin of internal resistance came into picture. Okay. Thus, the terminal voltage of the battery is 14 volts while its EMF is 16 volts. So, what is terminal voltage? You may have understood now what is terminal voltage. It is nothing but the voltage due to the external resistance, which is being voltage drops across the external resistance is nothing but terminal voltage. Thus, the terminal voltage of the battery is 14 volts while its EMF is 16 volts. The loss of the voltage, that is 2 volts, is accounted for the internal resistance 1 ohm of the battery. There is nothing but 2 ohms, 2 amperes into 1 amps, that is equal to 2 volts. So, hence this thing has also been explained to you. So, let me stop it here only. In the next lecture, I will start with the cells in series and parallel here, and then we will move on to the Kirchhoff's rules. So, let me stop it here. Thank you.